Hey, Chemistry Tribe. We are somewhat in a new module. We've already covered the first part of this idea of Module 11 with forces of attraction. And we talked about the notion of, the things that are in the solid state versus the liquid state versus the gaseous state, that we tend to have, very strong forces of attraction compared to, on the flip side, with gases, going from solids to gases, where we have very weak forces of attraction. So that's, kind of describing the idea of phases, and obviously liquids are in the middle. But what we have not talked about yet is this dynamic here in purple, going back and forth between the notion of these different actual phases. And so that's what we're going to get into now, as far as, the thermodynamics of phase change. So we really are looking at that idea of going between a solid and a liquid, and interplay between a liquid and a gas. And we'll even touch on the other ideas, such as going from solid to a gas, or vice versa. So we can describe these things. We've talked about this in the past, but we can describe these in terms of melting, we tend to like the term fusion in this case, or we're freezing, going the other direction. And then we have, the notion of going from liquid to gas, or vaporization. Please put your e-cigarettes away, right? But that is what vaporization is, going from a liquid to a gas. And then condensation, going the other direction. We do have sublimation and deposition, which is the solid to gas idea, but let's first just concentrate on these entities. So to begin, let's just kind of look at the idea of the vaporization state. And let's look at how vapor pressure and temperature the relationship between the two. And so we already know some ideas, right? First off, stronger force equals smaller vapor pressure. And then also the idea that vapor pressure increases with increasing temperature. And we also know that, the temperature when the vapor pressure of a liquid is equal to the atmospheric pressure. Is the boiling point. So those are some ideas that we've already talked about. And so there's just this inherent relationship between vapor pressure of a liquid and its actual boiling point. And there's actually this is actually a linear relationship. And so the Clausius-Clapeyron equation basically shows the linear relationship between the two. Right, the two being vapor pressure and temperature. And the Clausius-Clapeyron looks like this. We have the natural log of, pressure 2 over pressure 1 is equal to the negative enthalpy of vaporization over R times the quantity 1 over T2 minus 1 over T1. You might say, oh, this does not look like a linear fit, but indeed it actually is. In fact, we're looking at a slope here in terms of, here is our delta Y as far as the natural log of vapor pressure 2 over vapor pressure 1. So our y-axis is in terms of vapor pressure. And then our x-axis is off to the right. So there is our delta x. And so x here is 1 over temperature. And then what we find in the middle would be our slope, or often shown as m, where we have this slope, which is a constant. Our R value is our thermodynamic R value. And our delta H of vaporization, as much as the name describes, it's the amount of heat per mole to vaporize a molecule or element. So we've already talked about enthalpies, right, in terms of Module 9. And so that's just a very specific process, right? We're talking about with that vaporization going from the liquid state to the gaseous state specifically. So that's the Clausius-Clapeyron relationship. Basically relates vapor pressure to temperature. We know vapor pressure increases with increasing temperature, and eventually we then find that we have boiling occurring, reaching the boiling point. And that's also obviously related to the amount of heat it takes then to vaporize something, or to go from that liquid state to that gaseous state. So the Clausius-Clapeyron allows us to have a sense of, with a simple plot of vapor pressure versus temperature, we can solve for slope to get at the enthalpy of vaporization, or I can actually figure out the vapor pressure of a particular liquid at any temperature. And from the standpoint of trying to purify molecules and look at boiling points as a way to purify molecules, maybe by distillation, this is important, right? Because it allows me to figure out how these different temperatures affect vapor pressure and how I might actually find an avenue to separate, one liquid from another. So let's look at an example of this process. So to begin, we have toluene. Toluene is basically a liquid. And it has an enthalpy of vaporization of 38.2 kilojoules per mole. At basically 51.9 degrees Celsius, toluene has a boiling point of 51.9 degrees Celsius. Calculate the normal boiling point for the toluene. And so we need to, kind of remember normal boiling point would be at 760 millimeters of mercury, or 1 atmosphere. So here we have, a couple different relationships. We have the enthalpy of vaporization, and that might not lead us to where we need to go, especially when we get to the end of Module 11. But the fact that, apologize, we have a mistake there. The fact that we have this 2 temperature thing, we should have at 100 millimeters of mercury, toluene has a boiling point of 51.9 degrees Celsius. So please make that change. I apologize. But just from the delta H of vaporization, we don't necessarily know, given some other ideas, where exactly yet to go. But with the idea of the connection between temperature and vapor pressure, that now pushes us to this idea of using the Clausius-Clapeyron. So we could say we have a vapor pressure 1 with the 100 millimeters of mercury, and with our temperature below the 51.9, that could be our temp 1, right? Meaning that they're connected to one another. The vapor pressure of 100 is connected to the temperature of 51.9 degrees Celsius. And we want to calculate that normal boiling point. So we're really kind of looking for a temp 2, right? This additional boiling point, which now is actually going to be at our choice here. I'm going to stick with millimeters of mercury since we already have the 100 millimeters of mercury. But here would be our vapor pressure 2. in terms of the different values that we have. So all of that is really pointing to the expression of the Clausius, that we're really looking at a comparison of vapor pressure and temperature. And so as long as we're consistent with our substitution, we should be, fine. Meaning that I'm going to say that the second pressure is 760 millimeters of mercury, which means that that's going to go along with my second temperature, which is actually what I'm trying to find. And then I'm going to have an initial or another type of data point in terms of vapor pressure. In this case, 100 millimeters of mercury, millimeters of mercury, and that temperature, right, would be then our 51.9 degrees Celsius. But we would need to convert that into, into Kelvin. So we would have a value of 324.9 Kelvin. So let's make some more room here and get this correct. So here we have all the relationships that we need as far, and we know R, right? This is an old constant for us now of 8.314 joules per mole Kelvin. So that's why we need to get these temperatures at least into the correct units. For the vapor pressures, it doesn't actually matter as long as we're consistent. So here we're consistent in millimeters of mercury, so that's fine. But we wouldn't want to have one pressure in atmospheres and the other pressure in millimeters of mercury. So we just want to plug these values in and solve for the particular temperature. So we would have the natural log of 760 millimeters of mercury over 100 millimeters of mercury. That would be equal to the negative of our delta H of vaporization, which was 38.2 kilojoules per mole. And I'm going to change that right now to 38.2 times 10 to the third joules per mole. And that's because of our R value in that denominator. So we want to be careful here of units. One of them has to change. Delta H is normally a kilojoule game. So either you can change the constant to reflect kilojoules, or you can change the delta H. I chose to change the delta H. And then we'd have 1 over T2, because that's corresponding to 760, or our new boiling point. And then 1 over our 324.9 Kelvin. And so now we just want to go through the algebraic, mathematics here. Just be slow and stepwise. I'll start with the left. If I take the natural log of that ratio, I get 2.0281. If I look at my slope there, I would have a negative 4,594.65. That'd be times 1 over T2 minus then 3.0778 times 10 to the negative third. So I've done that reciprocal of the 324.9. If I divide over my 4,594, I get a negative 4.414 times 10 to the negative fourth is equal to 1 over T2 minus the 3.0778 to the negative third. And now bringing that 3 to the other side, I get a value of 2.63638 times 10 to the negative third is equal to 1 over T2, or that T2 is equal to 379.3 Kelvin, or if we convert it back to 106.3 degrees Celsius. So that would be the normal boiling point of the toluene. So that's how we can relate vapor pressures to temperature. This is a linear relationship. The linear relationship being the natural log of vapor pressure versus 1 over temperature. And then the slope allows us basically get to this idea of enthalpy of vaporization, considering that the R value is a constant. So we can get at that value by doing a careful experiment of measuring vapor pressure versus temperature. So now let's get into heating curves. And heating curves basically, are a representation of changes in physical states states of matter for a molecule or a element, as well as temperature changes within within physical states of matter. So a heating curve, tends to represent all of these. Here we could say, as an example, we have the heating curve for H2O. And we could look at this as, a pretty simple plot of our good old friend Q. Remember, which is heat. And then also temperature, which here we'll call degrees Celsius. So I'll kind of mark down, two important temperatures for, water being obviously 100 and 0 degrees Celsius. And what we find is we have, kind of a plot that starts like this. So let's start here at this, negative 10 degrees Celsius. So let's say we have, ice at negative 10 degrees Celsius. And so what are we going to do? Well, we're going to add heat to that. And as we add heat, what's going to happen, is our actual increase in temperature will happen as we add heat. And at 0 degrees Celsius is when we are going to observe a phase change happening. So if I just break down, really I see already two parts to this curve. Here is our first part. And if we look at the first part, we have ice. And it's going from negative 10 degrees Celsius to 0 degrees Celsius. And so we find what describes that would be something that looks like this. This is going back to our old calorimetry stuff from Module 9. That we have a specific heat capacity for the ice. and it would then increase in temperature according to the mass of the ice that we have, as well as then that temperature change. So we're looking at, that idea of specific heat, right? How much heat does it take 1 gram of material to increase in temperature by 1 degree Celsius? And so eventually we get up to 0 degrees. And so what we have now at step 2 is we actually have fusion, which is the heat required to melt a molecule. If we go back to that idea, our Q of fusion would be equal to moles times our delta H of fusion. So both of these are all old Module 9 ideas, right? The idea of something specific, such as ice and its increase in temperature, or then looking at a process, in this case, the idea of fusion or melting. So that's steps 1 and 2. There's then going to be another incremental increase, because once we are past that level of fusion, we now increase again up to the next temperature. And something important to understand, I guess, before we get to that third step, is to realize that when we are looking at ice increasing in temperature, it's just equal to mc delta T. But when we're looking at the heat required to melt the ice or the molecule, notice that temperature does not come into play. So that's something that's very important. Temperature is not part of a phase change heat. Only delta H, since basically you are breaking down the forces of attraction as we are going from, right, that solid state to that liquid state. So whenever we have that phase change, temperature doesn't come into play. So now we're past that, and we're at step 3. And so this is when we would be in terms of water. If we would look at step 1, we're talking about, ice. Now at step 3, we're talking about water. And it's very specific. So for step 3, if we're looking at water, going from, 0 degrees Celsius to 100 degrees Celsius, right? That's the whole transformation. We would have Q of the water is equal to mc delta T for the water. Remember, specific heat capacity is specific not only to the molecule, but also to the phase of the molecule. And then if we go back to our graph, we are at another plateau, or step 4. While earlier we had a phase change where we had, this type of flat surface or plateau, we find the same thing is going to occur here as we now go up in temperature, now trying to go past the next phase boundary. So now at this point, the heat that we're adding is actually causing the phase change to actually occur. So for 4, we have that idea of vaporization, right, which is the heat required to now go between the liquid and the and the gaseous phase. And so we find another very similar expression for now Q in terms of moles times our constant for our vaporization. And so again, there is our phase change occurring. If we go back, we could keep increasing because now we're in the fifth portion of the diagram. And now we've actually entered the gas phase, or in this case, we would say steam. And so the fifth portion would just be saying now we have steam going, from 100 degrees Celsius to, let's just say, 110 degrees Celsius. Regardless of those temperatures, as far as the 110, it could be higher than that. Our Q of the steam is equal to MC delta T. In terms of our specific heat capacity being for H2O in that gaseous state. So that is, the idea of the heating curve. And basically, just some notions within this, as far as, the magnitude of enthalpies basically indicate, the strength of these intermolecular forces. Right, the larger amount of delta H, well, the more heat's required. That means the stronger forces, because I have to break down a lot stronger forces, I need to have more heat for that process to occur. And just also, we want to basically, we're just using the same Q elements, if you will, from calorimetry. Right, so we can have Q is equal to negative Q and things of that nature. So let's do a hard example with this, I think. So given the enthalpy of vaporization for water is 40.66 kilojoules per mole. How much water basically can be heated from 20 degrees Celsius to 100 degrees Celsius? And how are we going to do that? Well, we're going to do that by condensing 1 gram of steam at 104 degrees Celsius to basically water at 100 degrees Celsius. So there is our question. So the first thing that we have to understand is that there are two things going on here. There are two processes. And the by here is really separating the two scenarios. So on one side of the fence, we have, this idea of how much water can be heated from 20 degrees Celsius to 100 degrees Celsius. And so to me, that looks like that's a Q, right? That's a Q specifically of H2O. And if I read that language carefully, I would say, well, the Q of the H2O liquid would be equal to MC delta T. I'd have to look up my specific heat capacity. They're asking me how much water, so that could be interpreted as mass. My C of H2O, when I look that up, would be 4.18 joules per gram degrees Celsius. And if I think about my delta T, I do know my temperatures. I'm heating to 100 degrees Celsius, and I start it from 20 degrees Celsius. So I have an 80 degree change. So I have a couple components already to that particular expression, right? As far as I know my C, I know my delta T, and I know those from these values I have below. So that's kind of the first thing. The second is we have this, by. So we're doing something else. We're condensing now 104 degree steam to water at 100 degrees Celsius. And I think something really important there to understand is we're going from a steam idea to a water idea. And so that's indication of a phase change that's occurring by just that nomenclature. So that's why we have at the very top probably this idea of the enthalpy of vaporization because of that phase change. So if we look at the other side, we could say, maybe looking at the Q of the steam now, that there's actually two things going on. There's the MC delta T for the steam, because if we're looking at our specific heat capacity, well, we do have that being 1.84 joules per gram degrees Celsius once we looked it up. And we also have that temperature change occurring as well, saying that, well, we were at 104, and now we're going to 100 degrees Celsius, so we're seeing a drop in temperature. So guess what? There's that idea of heat flow, right? It looks like the heat, the water is increasing because it's going up in temperature. Well, that means where is it getting that heat from? It must be getting it from the steam, because the steam is actually dropping in temperature. But we also, right, have that idea of the phase change. Meaning that Q is equal to moles times our enthalpy of vaporization. And we know what that enthalpy of vaporization is. It's equal to the 40.66 kilojoules per mole. So we also have other things, right? We know the mass of the steam is 1 gram. So we have that as well. And we could also say we actually know moles of the steam, because if we would take, moles would be taking that 1 gram and dividing it by 18 grams per mole for our H2O to give us 0.0555 moles. So in looking at these values, we have all of them, right? We have the specific heat for the steam. We have the delta T for the steam. We have the mass of the steam. So we can figure out Q of the steam. We also know the delta H of vaporization. So we know what that is in terms of the other expression. And we also know our moles of steam. So again, we know our other Q. So really, with all of this, we have everything except for what we see off to the far top left corner, which is the mass of H2O, which we're actually looking for. So what we can say here is that the Q of the H2O would be equal to the negative Q of the steam. Again, there's that equal but opposite in magnitude. One is the system and one is the surroundings. So if we wanted to keep this in blue, we could, keep our steam in red. We can do that as well, but we just need that negative sign to show the inconversion between, the system and the surroundings motif. So we could say then that our MC delta T for our water is equal to negative our MC delta T for our steam plus moles times our enthalpy of vaporization. Right, taking all the components from one side, all the components from the other, and then having this equal in magnitude but opposite in sign. So we can start to plug in these values that we have. We have the specific heat capacity for the water, the 4.18. We have the 80-degree temperature change for the H2O. It's increasing in temperature. We have the 1 gram of the steam. Its specific heat capacity of 1.84 joules per gram degree Celsius, and its temperature change of negative 4 degrees Celsius, plus then our 0.0555 moles, which is our mole value for the steam. I'm just trying to make a little bit more room here. And then we have that multiplied by the 40.66 kilojoules per mole. Now, one thing I need to highlight here as I'm writing it in is the sign of the value being, a negative and not a positive that we see above. So I want to talk about that. Now, in going back, realize that the steam is not vaporizing, right? The steam is condensing. So we're really looking at a change of that idea of the sign of the 40.66. That's specifically for vaporization. But really what we need here is the delta H of condensation. And that's just the flip of the sign. And so that brings together everything that's going on with the actual steam. We have the heat decrease for the steam, and then we have the phase change for the steam that's occurring. So that's our reason for sign change. So if we're just kind of slow and stepwise here, I would have the mass for the water that I'm looking for times, 344.4. I guess that would be in terms of joules per gram at this point. I have my negative sign in front of the brackets, and if I do each one individually, I would get a negative 7.36. Excuse me. Joules. And that would be plus then a negative 2.2566 kilojoules. So let's be careful with that notion. Right, our mass would be 3 times 334.4 joules per gram. I just want us to be careful with that conversion that we see on the other side. We want to make sure that we're in the same units of joules. So we could have, tens times the third joules. And so just, again, kind of plodding away here, we have our joules per gram. We now have our total energy on the right side, and that would be a negative 2,263.99 joules. Obviously, we're going to have that sign switch occurring. And if we divide over our joules per gram, the 334, we end up with a value of 6.77 grams of H2O. And that, to be honest, is how a lot of, we get our hot water on UVM campus. We have a lot of steam tunnels underneath UVM campus, which are condensing steam. And where is that heat going? Well, that heat is going to then heat water systems so that we have hot water for our showers, etc. So that's the idea of heat flow, in conjunction now with the idea of heating curves and looking at the full gambit in changes of state. The last bit of the module is looking at phase diagrams. And so I just want to break down what a phase diagram is and the different pieces to it. Phase diagrams basically give us a good representation of how pressure affects melting point and boiling point. As well as sublimation point. So now really getting into all the phases. The general plot that we have is in terms of pressure versus temperature. And what I'm going to represent here crudely is this is H2O. And so H2O kind of has this straight line. We then have this acute angle going off to the left. And then we have this kind of nice curve. And so there's a couple points that we find are part of the curve. And we always find this type of distribution of phase. So here we have the liquid phase, the solid phase, right, the gas phase. And if we say, for instance, our pressure here is 760 millimeters of mercury, or 1 atmosphere, that's where this idea of normal points, as far as normal boiling point or normal melting point, actually come into play. So here would be our melting point, and then here would be our boiling point in terms of our temperature, right? It corresponds to the phase change, going from one side to the other, going from solid to liquid. If we're at 760 millimeters of mercury, well, then I know the temperature for that melting to occur. Or if I go even further, I can now figure out the boiling as far as liquid to gas. Some other points that we have there would be the triple point, which is basically the temperature and pressure, where all three phases exist simultaneously. And then way out on the end, we have what's known as the critical point. Basically, past this, we have a new phase, which is known as supercritical fluids. And these are basically gases that behave as liquids. So we have some combination of properties there because of our high temperature and also our high pressure. So that's supercritical fluids. So this chart really allows me to kind of look at all the different phases with pressure, meaning that if I increase the pressure, notice that because of that slant between the solid and the liquid, it's going to the left. So if I increase my pressure and going up, that means I actually am lowering the melting point. Same with the other way. Like if I go way out, realize that as I am increasing that pressure, I'm also increasing the boiling point. But if I decrease the pressure, I'm actually decreasing the boiling point. And so this helps us to understand all of these, ideas of phase change, in terms of going back and forth here as far as that notion of, melting and freezing. Or going in this maybe direction where we're talking about, condensation or vaporization. And then also it gives us the third ability to now go between all of the phases where we're talking about deposition and then sublimation. And so that is basically our phase diagram. And so it gives us a way to represent temperatures with specific phase changes, but also with regards to pressure. So that means we as chemists can simply change the pressure of our system, and that has now an impact on all of these types of points, as far as sublimation point, melting point, freezing point. And now that gives us some very distinctive power in being able to separate molecules from one another, because molecules are going to have different temperatures that they boil at or melt at or sublime at. And so if I have that information, I have the ability to augment my system by changing the pressure to then impact, the type of purification process I want to invoke. And so this gives the chemist a lot of power as far as understanding the pressure relationships to the temperature for the phase changes that occur between solid, liquid, and gaseous state. And that is Module 11.